Okay, so welcome to Le Chatelier's principle. This is one of my favorite lessons. So now we're going to look at what happens when an equilibrium system is going to change. So not every reaction can exist in balance. So again, those of you that are into biology, so you'll talk about homeostasis, like everything, your blood can't be a pH of 7.4 always. There's all kinds of things that you eat that are acidic or basic. And so our body has to have a way to adjust to get back to the balance or the equilibrium or the homeostasis. So that's what we're going to look at today. So Le Chatelier is a person, and he described how you can predict how an equilibrium system is going to change based on certain stresses. So in the title here, it says qualitative. So we're going to do qualitative changes today. And then when we get to 7.5, that will be quantitative changes. So doing math. Okay, so when you have equilibrium, that means the concentration of products increases, reactants decreases. That is the forward reaction. And then when you start to increase the products, then they are able to collide, those particles, and then that concentration will go down. The reactant concentration increases, which we consider to be the reverse reaction. And then when they are equal, that is equilibrium, chemical equilibrium. So when you have forward reaction occurring just as much as reverse reaction. So one of the conditions from 7.1 we talked about when equilibrium is recognized is when all observable macroscopic properties are constant. So if there is a change in color, then it's easy to see the equilibrium has been stressed, pressure, concentration. So those are the things that we're going to use today. Okay, so let's say we had this reaction here. So on the left, or the reactant side, it says that they are colorless. And then on the product side, it says that they are brown. So if the equilibrium is shifted, so we'll talk about 3 different types of stresses today that can make an equilibrium either go to the right or to the left. So if we were in class, I would actually get you guys to make little signs that say right or left, and then we would talk about what the stress was and try to predict whether it was going to be right or left. If you are the kind of person who does not like directions, so shift to the right is the forward direction. So you can think of it like forward instead of right. Excuse me. And then a shift to the left would be the reverse is favored. It doesn't really matter. You do whatever you choose. So a really easy way to tell whether the right or left or forward or reverse has been favored if the reaction has a different color is a change. So it says the shift to the right means that you would get more brown color, and then a shift to the left would be a reduction in brown color, so less brown or back to colorless. So that's what we're going to look at. What happens if you go forward? What would you see? If you go reverse, what would you see? Okay, so Le Chatelier's principle by definition means that if a stress is brought upon a system at chemical equilibrium, the system is going to shift to minimize or offset the stress. So shift means like one side favored over the other. And now I actually know that there was going to be something in there, isn't there? So the system is going to adjust in a way to oppose the change. So for example, if you stay up all night, and that's a stress, what does your body want to do? It wants to go to sleep. Okay, so it's going to adjust in a way that opposes the change. So when you have Le Chatelier principle and applying that, then you have an initial. What does the initial state look like? So is it brown? Is it colorless? For example, then what's the change? What's the shift going to be? And then what is the new equilibrium state? So actually what we're going to do when we get to 7.5, we're going to do math, doing an ice table. I for initial, how does it change? And then what's it at equilibrium now? Okay, so that's what we're moving towards. So, but today we're just going to use the principle to predict the response of the system in a qualitative way. Okay. All right, so we're going to look at stresses now, and we're going to do 3: temperature, concentration, and pressure and volume. And we're going to start with temperature, which is actually the hardest, okay, or requires the most brain power. All right, so when you have a system, there are 2 possibilities. So you either have endothermic, and that means energy is a reactant, or the delta H is going to be positive. So in the worksheet, I know some of the questions are going to give the delta H value as either positive or negative. And then if you have exothermic, energy can be listed as a product, and the delta H is negative. So the reason that temperature as a stress requires the most brain power is because you could have endothermic or exothermic, so that's 2 choices, and then the temperature can be increased or can be decreased. So then that adds in more possibilities. So really try your very best to try to understand what's going on, as opposed to just memorizing, because that's difficult to keep all straight. When you have when you talk about temperature, so the stress could be listed as increasing heat or increasing temperature or increasing energy. All of those are equivalent. Okay, so energy is either, like I said, there's only 2 choices. You either heat it up, you add energy, or you cool it down, or you removed it. So then if the system is cooled, then that is the stress. So then it's going to try to warm itself up. So it's going to shift or favor one of the sides that is going to produce heat. Okay, so Le Chatelier's principle, it's always opposing the change. So if the system is cooled, if that's the stress, then the opposite of cooling is warming up. And then that vice versa. If you add heat, so if that's your stress, the equilibrium shifts in the direction that absorbs heat, or so we can cool down, or the system can cool down. Okay? So that's why it's important to note endothermic heat is a reactant, or on the reactant side, or the reverse direction. And then exothermic heat's a product, or on the right-hand side, or favored by the forward direction. So there is quite a few ways to think about this. Okay, so we have this example here, and here we have the energy listed. It says E. It could say energy. It could give you some kind of kilojoule value. It doesn't matter. But this is an endothermic reaction, but that actually sort of doesn't even matter, okay? So what this is saying is if the energy is a reactant, that means that going in the reverse direction is going to produce energy. This is weird because normally so far when we've done exo and endo, we've done reactions in the forward direction only. So we did calorimeters, and if you had an endothermic reaction, it felt cold, okay? So when you do these kinds of questions, so let's say we're gonna heat this one up, then you're looking at which direction produces heat or has heat and which direction does not, okay? So if the system is heated, that means that in order to oppose the change, it has to cool down. So again, you kind of have to force your brain to think in double directions, which we have not really done before, okay? So if you go to the right, like if you favor this direction, there is no energy listed on the right-hand side, which means no energy is produced in the right-hand direction. Okay, so that is going to cool the system down. So the system is going to shift to the right or forward if you don't like directions. Okay. Another type of question you could be asked is what happens to the concentrations? So if we shift to the right or forward, then that means that the concentration of the product is going to increase. And in this case, the product is NO2. Okay, so one more time. When the system is heated up, the opposite has to cool down. If you look at the reaction, no energy is produced on the right-hand side or the forward direction. So that means that favoring that side or shifting to the right is going to not make more energy. So it wants to cool down. It does not want to warm up. Okay, so now we're going to do another one. And here this time we have energy on the product side. Okay, so now, and we're going to cool our system down. So if you cool it down, it has to warm up. So you're looking for the direction that energy is produced. Okay, so if you go in this direction, there's the energy. So that means energy is going to be produced when you shift to the right. So this one is more what you're used to. So even in the other example, when you have endothermic, you would think that it would cool down. So because that's what you're used to, going in the forward direction. So this question makes a little more sense because the equilibrium is cooled down, which means that if you want to warm up, it has to shift to the right. So you would probably know that in an exothermic reaction, which is what this is, then you would consider that to be producing energy because we're used to going only in the forward direction. Okay, so try to use things that you've already seen, but the temperature definitely does require the most brain power. Okay, and then so again, if you're shifting to the right, the concentration of SO3 is increased. So when we did the other one, it was also shifted to the right, but it was the opposite stress heat. We heated it up instead of cooled it down, but it was also the opposite kind of reaction. So that's why, like I said, it's it can get very hard to try to memorize it. Try to think about what kind of reaction you have and whether you're trying to produce heat or not. Okay, on to pressure and volume. So pressure and volume is you have to look and make sure it only affects gases. So you want to look for in the reaction the little g, okay, which makes sense. You can't really change the pressure like by compression of a solid very easily, right? So only affects gases. And what's going to happen is we're going to consider a change in the volume. So pressure and volume, yes, they go together if you remember from grade 11, but I think it's easier to think about volume first. So if you have usually I use the example with you guys in the classroom as gas particles. So if we're in a big classroom and we have lots of gas particles, is there a good chance that you're going to collide with each other in a huge classroom? Maybe not. If I try to shove you underneath a desk, all of you gas particles in a little tiny volume, is there a greater chance that you're going to collide? Yes, there is. So pressure is an inverse relationship. So when volume increases, pressure decreases, or when volume decreases, pressure increases, vice versa. Okay? All right, so let's say you're increasing the volume, then pressure decreasing, that goes with it. but I think it's easier just to think of the volume. So when volume increases, that means you've got more space to fill up, because you want, and you want the pressure to, you want to oppose the change. So you want the pressure to actually come up. So then we need more, if you have more space to fill, we want to fill it the fastest to offset the stress. So that means we're going to shift to the side that has more moles of gas. And all you have to do is look at the coefficients. Sorry, that was terrible. Okay, so on, let me see if I can get a different color. No. On the reactant side, we have 2. And on the product side, it's understood there's a 1 here. Which side has more moles? The left-hand side does. So more volume increases, more space, more moles of gas in order to bring the pressure up at the fastest. And then, so you're going to increase the pressure as more particles are produced, relieving the stress. So shift left, or again, if you don't like directions, do reverse. Okay, so then the reverse is true. When volume decreases, it's going to shift to the side with less moles, because now you have less space to fill up. So in our example here, the lower amount was on the product side, so the shift is going to be to the right. So then the pressure will be decreased because you're making less molecules, relieving the stress on the equilibrium. If there are equal amounts of moles, but remember, you're only looking for gases, so the ones that say G. So if there are equal amounts of moles on both sides, then there's no shift, okay, in the equilibrium. No effect, you can write, or no shift, because there are equal moles on both sides. They would both be changed equally. Okay, concentration is sort of the easiest. All you're doing is, if you increase the concentration of a reactant or product, it doesn't matter, then it's going to shift to use it up or decrease it. And then vice versa. If the concentration's decreased, then it's going to shift to replace it or to make more. Okay, so now we're back to this one that was in 7.2. So if you add more N2 or H2, now be careful, because let's say you have to list the changes to shift to the right or something. This counts as the same. These are both reactants, so you can write out specifically N2 or H2, or you could just actually write more reactants are increased, and it's actually the same thing. Okay, so let me see here if I can, whoops. I'll just move that over. Okay, so that's a shift to the right to consume it. So on the right-hand side, then there is, your shifting to the right produces NH3 and uses up the reactants, which is what you want. Okay, you can also think of it in terms of collisions. There are more collisions between N2 and H2 if you increase the concentration. So then that's going to, when you have more collisions, of course, that's the same as the last unit, the rate is going to increase. If NH3 is added, So now you're increasing the product. So again, you can just write product, or you can write the specific thing. To the left, to the left. It's going to shift to the left. To the left, to the left. I didn't realize that was in there. You can thank Mr. G for that. So it's going to shift to the left because now the reverse is true. So now there's more NH3 particles able to collide and decompose into N2 and H2. So the reverse reaction becomes greater. So if you don't like left, then talk about reverse. Okay, so there are a couple of things that do not affect the position of equilibrium systems. So you can add a catalyst. The catalyst just makes the reaction happen faster. A catalyst, if you remember, is not an overall product or reactant, so it doesn't change any of the concentrations or anything like that. Everything just happens faster. When you have, so this inert gas, so when I was in high school, we called noble gases inert gases because we could not naturally get them, they didn't naturally react, which is still the same, but now in a lab, we can force big ones like xenon and radon to react. So we had to change the name, but the principle is still the same. So in a natural way, it's not going to affect the position of the equilibrium because because the probability of successful collisions is equal, and by successful collisions, because it doesn't react, there are none. So there is no shift. Okay, so usually when you add a gas, you would think of like the volume or the pressure changing, but if it's a noble gas, then that's not the case. Okay, so here are the homework questions. They are also listed in the submodule. It says Monday, April 6th. Okay, so they are listed there. The worksheet is provided there. So the solutions for the textbook questions and the answers to the worksheet are also there. Usually what I do in class is we add in this chart to do one more example. Okay, so if you want to, I think if you printed the notes off, there should be more than enough room there to add this into your note. That's usually what students do. Okay, so if you want to pause the video and get that down, and then we'll take this up. Okay, so this is what we're going to do is we are going to we've been given stresses. We're going to explain what happens, and then we'll look at the direction of the shift, and then we'll look at the size of KEQ. Okay, so if you increase the concentration of SO2, so that is a reactant, which means that you need to consume it. So if it shifts to consume it, then it's going to shift right. Because on the right-hand side, there is no SO2. We're going to be making SO3. Okay, so sometimes people like to think of it like you're balancing it out. So if you increase something on one side, then you have to increase the substance on the other side because then that balances it out. That's fine to do as well. If you're into just the opposing changes, that works well too. Okay, so you increase the concentration of SO2. What's the opposing change? Decreasing it or using it up. Okay, we didn't really talk about the size of KEQ yet. So if you remember, KEQ is products over reactants. So you can estimate what's going to happen to the size of KEQ based on the shift. So when you do this, think about what would happen to the size of KEQ right after the shift. Okay, so if you shift to the right, the products are going to increase. So if the top of the fraction increases, right, because it's always products over reactants, then that's going to make our number, our KEQ, larger. So we have no idea what it was. So we can't say greater than 1, less than 1. We don't know what it was. We're just saying that if it shifts to the right, then the products are going to increase when you have a fraction and the top of the fraction increases, that makes the overall answer increase. Okay, so I've used short forms here. Sorry if that bothers you. So we're decreasing the temperature. So what does the system have to do? It has to shift to warm up or shift to the side that makes heat or energy. So this question, here's the heat on the product side. So that means it's going to go right. Oh, I forgot. If you don't like directions, you could call that forward. Okay, so it shifts to the side that produces heat, which is right or forward. So it would increase as well. Okay, so then if you, like I said, pressure and volume go together, but it's sort of easier to think about the volume. So if the volume decreases, it has to shift to the side with more moles. Okay, sorry, less moles. What am I saying? Okay, because of the decrease in the volume. So which side has less moles? So this side has 2 plus 1. Check that they're all gases. Yep. This side has only 2. So then again, it's another shift right. Okay. So this is supposed to be helium, which is a noble gas. So no shift. Oh, let me just write. So no change in the size of KEQ. Same thing with a catalyst. Okay, so again, no shift and no change. Okay, so try as many questions as you can. Tomorrow when we do Le Chatelier graph, we'll look at it again in a different way to represent it, and it might actually